Hello, and welcome back to our Calculus 1 series. In today's video, we're going to build on the discussion from the previous lecture where we talked about real numbers, set notation, and interval notation. Specifically, we're going to be focusing in on inequalities and interval notation, and I'm going to work through a variety of example problems ranging from easier to more challenging problems so that we can get a better hang of these problems. So yeah, let's begin. If you recall that an inequality or an equation with inequalities is any equation regarding or with these Boolean operators. So less than or equal to, greater than or equal to. So in the last video, we defined some rules for these inequalities, and I see one error straight away. Let me redo rule number 6 for you, 0, A, and B. But let's say that A is, and B and C are all elements of the real number system. Then we can define these rules, and I'll go quickly because we reviewed this in the last lecture. But we have A plus C being less than A plus B, which makes sense intuitively if you're just adding a constant to both sides. Oh, sorry, this is B plus C. If you're adding a constant to both sides, you maintain the inequality sign. And likewise, A minus C is less than B minus C when A is less than B. Again, makes sense intuitively. You're just taking away a constant from both sides, so you should maintain your inequality sign. When we have A less than B and C bigger than 0, we have our scaling rule, meaning AC would be less than BC. You're just multiplying both sides by a positive scalar, so your inequality should be maintained. This is the first one where we have an inequality change. If we have A less than B and C less than 0, we'd have AC being bigger than BC. And this is because negative A would be bigger than negative B. Let's think of an example quickly. If you have, let's say, C equal to -1, A being equal to 2, B is equal to 3, we know right away that 2 is less than 3. But if we multiply by -1, both sides by -1, we introduce the C, then we get -2, and that has to be bigger than -3. So that makes sense that we'd have a sign switch when we multiply by a negative scalar. The next one, where we have A is bigger than 0, we'll have then 1 over A bigger than 0. I think that one makes sense intuitively. And last but not least, we have A being bigger than 0, but B being bigger than A. And we have 1 over B is less than 1 over A. And I guess a demonstration for that would be, let's say we have A is equal to 2 and B is equal to 3. Then we know 2 is less than 3, but 1 over 2 is bigger than 1 over 3. This is 0.5, and that's 0.333. So we know that this rule holds true. So knowing this, let's go into some example problems right away where we will face some easier to more challenging inequality problems that you could encounter in your calculus course. So for the first example, example 1, let's say that we have 5x minus 3 less than or equal to 7 minus 3x. So how do we do this? Solution. If you recall, we just use our simple rules of algebra to solve for x. We isolate x on one side and everything else on the other side, and we solve. So let's do that. Feel free to pause the video and solve the questions yourself, and then come back to it to check to see if you got the right answer or not. So in this case, we bring all the x's to the left side, and we bring all the constants to the right side. So we'd have 5x plus 3x, and that would be 7 plus 3. We then have 8x is less than or equal to 10. X is less than or equal to 10 over 8. And that's equivalent to x is less than or equal to 5 over 4. Great, pretty simple, relatively easy. If you guys recall how to represent this in interval notation, again, let's draw a number line quickly. Let's put 0, 1, 2, -1. We have 5 over 4 approximately right here. We'd fill in the circle because we have the less than or equal to sign. And then we go all the way to -infinity because there's no bound on it. That being an interval notation, I'll write it like this, in. We have -infinity, open bracket, since -infinity is not necessarily a number. And then we go to 5 over 4 in a closed bracket because, or a square bracket, sorry, because we have a filled in circle. And again, we have that sign right there. And that's your solution. Relatively easy. Let's go to the next problem. So next problem, again, going to be similar level, not too hard. 3 less than or equal to 2x plus 1 less than or equal to 5. In the last video, I showed that you could solve this by taking each part. So you could take this side and consider it, and then you could take this and solve like that. But you can do multiple ways to solve this problem. We'll try solving it simultaneously this time. So what you're going to do is subtract 1 from all sides. And when I mean all sides, I mean this, and this, so that we're isolating for x to be by itself. So you'd have 2 less than or equal to 2x less than or equal to 4. And then we'd divide everything by 2. So 1 over 2, 1 over 2. And that gives you 1 less than or equal to x less than or equal to 2. That's great. Now let's put this in interval notation and on a number line. So on a number line, we'd have, let's put 0, 1, 2, 3 on the number line. Have it like this. Oops, sorry, that's past 2. We go all the way to 2, including the endpoints, by filling in the circle because we have the less than or equal to and greater than or equal to signs. In interval notation, that's easily represented as 1 to 2 with square brackets, meaning that we have a closed interval. Great. Moving on to the next problem. Again, that was pretty easy. We're going to step up the complexity a little bit. Not the hardest problem, but you'll see that it requires a bit more work. X squared minus 5x plus 6 less than 0. So this is known as a quadratic inequality. So how do we approach this? Well, we're going to simplify the problem again. So if you remember from your pre-calculus courses in high school, how to simplify or how to factor polynomials, this is what we're going to do. So x squared minus 5x plus 6. We know that x minus 2 and x minus 3 is equivalent to this. If you recall, then you need to have two numbers that add to -5, and these two numbers also have to multiply to 6. That is -2 and -3. So now we write down the roots of our equation. Roots. We know intuitively that x is equal to 2 and x is equal to 3 are the roots of the equation, where the equation is equal to 0. And let's draw this on a number line. So I have 1 here, 2, 3, 4. So we have this is one of our roots, and this is another of our roots. What we can do then is look at all the different intervals we've created by separating the real number line by our roots. What do I mean by that? We will analyze the inequality in 3 different cases. Case 1, case 2, and case 3. So case 1 is from 2 to -infinity. Case 2 is from 2 to 3, and case 3 is from 3 to infinity. Let me put 3 right here. So let's start. Let's analyze case 1. So to analyze case 1, we need to use a test value of any number inside that interval. So let's try that. Let's use 0, because 0 would be over here, and it's inside the case 1 domain. So case 1, x is equal to 0. So when x is equal to 0, what does this inequality look like? Well, it turns out the inequality looks like this. And it needs to be less than 0. Well, it turns out that we can analyze the signs of each of these components. I know you could just solve it very easily, but I find that this is more efficient when you find harder problems down the road, that you can tell that this is negative and that this is negative. A negative multiplied by another negative gives you a product of a positive. So the entire value is positive. And we know a positive cannot be less than 0. We know that this can't be true. So we say that this is false. Case 1, I'll put an x beside it. We can't have anything in case 1. Let's try case 2. In case 2, let's take 2.5. It's a good value. If you can't really work with decimals, then you can use fraction. 5/2 is equivalent. Any value inside 2 to 3 domain, between 2 and 3. Don't use the endpoints, however. I will say do not use the endpoints because your endpoints are your roots. Look for any value in between. We'll deal with the endpoints at the end. So for case 2, x is equal to 2.5. So when we plug that into our inequality, we have 2.5 minus 2. And we have 2.5 minus 3, and that's less than 0. Let's make our less than sign better. It's not the best. Less than 0. So when we analyze this, we see that this value is going to be positive. 2.5 minus 2, we know that's positive. But 2.5 minus 3, we know that's negative. So the value of the product of a positive and a negative is a negative. A negative is always going to be less than 0. So we know that's true. That this case is going to be part of our solution set, our set of solutions. So let's put a check mark beside case 2 because it works. Scroll down. Case 3. Let's say x is equal to 4, since that's in the domain of case 3, between 3 to infinity. With x is equal to 4, we get 4 minus 2, and we get 4 minus 3 less than 0. You could probably already tell this is positive because the value is 2. This is positive. The value is 1. So the final product, a positive multiplied by a positive, is obviously a positive. We can't have a positive being less than 0. This inequality does not hold true. So we say that this is false. And that's it. We see that our only case that satisfies the inequality is case 2. So that's our interval. That's our solution. So then in interval notation, we write that the solution is 2, 3. What brackets will we put around 2 and 3? Let's think about it. If we have, let's say 2, if we use 2 in our inequality, x minus 2 and x minus 3 are less than 0. So let's say x is equal to 2. X is equal to 2. Then we'd have 2 minus 2 and 2 minus 3 less than 0. But this is 0 because 2 minus 2 is 0. So we have 0 is less than 0. That's not true. That's not true. And the same thing would happen if we had 3. If it was a less than or equal to sign or a greater than or equal to sign, then we can include our endpoints. But since the sign does not equal to, since it's not a less than or equal to sign, then we can't include our roots. We can't include those endpoints. So then on our interval notation, we'd have to include the round brackets. And that would be our solution. It's important to notice your endpoints when you're solving these problems. So not terrible, but definitely more involved than the first two examples. Example 4. So example 4 is going to be a little bit more involved. So we're getting a bit more challenging again. X less than 2 is greater than or equal to 1 plus 4 divided by x. So again, we want to have all the x's onto one side. And moreover, let's have an entire expression be greater than or equal to 0. I feel like that's easier to work with. So what we would do is bring everything to the left side. So we have x over 2 minus 1 and minus 4 over x. And that is all greater than or equal to 0. Then what we want to do is create a common denominator. So all of these values will have to be on the numerator divided by 2x. So let's set that up. So 2x, and let's go greater than or equal to 0. And let's give myself a bit more space. So for this first term, to make this possible, we need to multiply that by x. So we'd have x multiplied by x, that's x squared. The next term, we need to multiply by 2x, so we'd have minus 2x. And the last term, we need to multiply by 2. So it'd be negative 4 times 2, negative 8. We then want to factor the numerator. So when we do so, that becomes negative 4 and positive 2, x minus 4 and x plus 2 all over 2x. And again, that's just because two numbers that add to negative 2 and multiply to negative 8, negative 4 and positive 2. So now we look at our roots. We have x is equal to 4, negative 2, and 0. Let's put our roots on a number line. So let's put negative 3, negative 2, negative 1, 0, 1, 2. I'm running out of space. 3, 4, 5. Sorry for it not being completely the neatest, but there we go. And let's separate our real number line into separate cases. So we have everything after negative 2. We have 0, which is one of our roots, and we have 4. Just recall that 0 is one of our roots because we have this. It's not on the numerator, but that is one of the points that we need to include because 2x is equal to 0. When 2x is equal to 0, that is a switch point. So now we're going to analyze case by case. So we'll have case 1, case 2, case 3, case 4. Great. So case 1, when everything is less than negative 2, let's use a test value of negative 3. I feel like that's x is equal to negative 3. I feel like that's a good value to start with. So then we'd have negative 3 minus 4, negative 3 plus 2. 2 and negative 3 has to be greater than or equal to 0. So instead of solving it all the way again, let's just analyze the signs of each of these. So we know that this right here, that's negative, that is negative, and this is negative. So a negative multiplied by a negative, that's a positive. So on the top, we have a positive. But divide that by a negative, we have a negative number. A negative number can never be greater than or equal to 0. So we know that this is false. So that eliminates case 1. Let's put an x by case 1. Case 2. Let's say x is equal to negative 1. It's an easy one. So we have negative 1 minus 4, negative 1 plus 2, 2, and negative 1. myself a bit more room. Say it's less than or equal to 0. So we know that this value right here is negative. This right here is actually positive, and this right here is negative. A negative multiplied by a positive is negative, divided by a negative is positive. Oop, this sign is incorrect. Sorry, everyone. But yes, as I was saying, a negative multiplied by a positive is a negative, divided by a negative is a positive. Therefore, we know that this is true. So let's put a check mark by case 2. Looking at case 3 now. Case 3, let's use the value of 1. So x is equal to 1. In this case, we'd have 1 minus 4, 1 plus 2, 2 divided by 1, all having to be greater than or equal to 0. When we analyze this, we see that this, is negative, this is positive, this is positive. So a negative multiplied by a positive is negative, divided by a positive is negative. So everything is negative. We can't have a negative number being greater than or equal to 0. So we know that this is false. Let's put an X beside that. Last, but certainly not least, case 4, with an x value of equal to 5, since that's greater than 4, we're going to have 5 minus 4, 5 plus 2, all divided by 2 and 5. This all has to be greater than or equal to 0. Well, it turns out that this is positive, this is positive. When I mean this, I'm talking about this root, and that root, and that on the bottom is all positive. Positive multiplied by positive is positive, divided by positive is a positive value. All positive values are greater than or equal to 0. So we know that this is true. Put a check mark here. So now we have our intervals. Great. So we have everything between -2 and 0. But how do we also represent what's on the greater than 4 side? We can use something called a union, a U or a union, to represent that we have values across different intervals on the real number set or on the real number system. So we can have different intervals broken up as long as they're set intervals. So the interval between -2 and 0 works, and the interval between 4 and infinity works. So we'll have a union 4 to infinity. And let's bring this down. So what about the endpoints? We know that infinity needs to be represented by this, but what about 4, -2, and 0? What would they look like? How would the endpoint behavior look like? Well, since we have the greater than or equal to sign, if we use the values 4 and -2, it will turn out that we'll have 0 greater than or equal to 0. I'll show you what I mean by that. So let's say, for example, we have 4 minus 4, 4 plus 2, 2 and 4, greater than or equal to 0. Well, this is 6, but this is 0, and this is 8, but 0 times 6 divided by 8 is 0. So you're left with 0 is greater than or equal to 0. But that's true because we have the greater than or equal to sign. So for 4, when we have x is equal to 4, let's say when x is equal to 4, we have it being the endpoint being part of that solution set. So we can include the closed bracket. And the same is true when we have -2. What about with 0? We can't do that with 0 because recall, 0 on the denominator makes this point discontinuous. It's not possible to have 0 at the denominator. 0 cannot be a part of the solution set. So we say that with a round bracket. So our solution set, our an interval notation, looks as such. -2 to 0 and 4 to 8 with with round brackets around 0 and square brackets on -2 and 4. Let's do one more example. Just to drill home the learning. And again, it's going to be similar to the last problem. So we have x being less than or equal to 2 plus 9 over x minus 2. Okay, let's bring everything to one side like we did previously. So we'll have x minus 2 minus 9 over x minus 2, all being less than or equal to 0. Great. Now let's get a common denominator. So to do that, we would have x and x minus 2 minus 2x minus 2 minus 9 all over x minus 2. If you don't know how I did that, it's fine. You just got to review on some of your algebra. In my first video, I talked about the importance of being aware of your algebraic skills, your factoring skills, this type of stuff. So this is kind of where it pops up again in your calculus course, being able to manipulate your equations to get them to forms in which you'd like. So let's simplify this. We get x squared minus 2x plus 4 minus 9 all over x minus 2, just from simplifying the top. Then combining like terms, you have x squared minus 4x, and we have minus 5 all over x minus 2. It's not equal to 0. Finally, we're going to have x, do this in my head, x minus 5. Let's have x plus 1 all over x minus 2. And that's got to be less than or equal to 0. Perfect. Now let's look at our roots. We'll have x is equal to -1, x is equal to 2, and x is equal to 5. Perfect. So let's put that on a number line. We're going to have -1, 0, 1, 2, 3, 4, 5, 6. Really good. Let's break this up into the different intervals. We'll have -1 here, we'll have 2 here, we'll have 5 as such. Case 1, case 2, case 3, case 4. Now, just like the previous question, we break it up all into different, we break up the different cases using testing values that we'll use from x in each interval, and we check our inequalities. So case 1. Case 1, let's say x is equal to -2. Then we'll have -2 minus 5. And I'll go a bit faster in this example because you should have it by now. All over -2 minus 4, or minus 2, sorry. It's going to be less than or equal to 0. So it turns out that this is negative, this is negative, that's negative. A negative multiplied by a negative, that gives you a positive divided by a negative. It's a negative. So in total, a negative value, and that's always going to be less than or equal to 0. True. Case 1 is good. Case 2, x is equal to 0. We get 0 minus 5. 0 plus 1. 0 minus 2. Less than or equal to 0. This is a negative. This is a positive. This is a negative. A negative multiplied by a positive, that gives you a negative. Divided by a negative is a positive. So everything here is positive. Positive cannot be less than or equal to 0, so we say that this is false. Case 2 does not work. Case 3. Let's pick x is equal to 3. So we get 3 minus 5, 3 plus 1, all divided by 3 minus 2, less than or equal to 0. This is negative, this is positive, this is positive. A negative multiplied by a positive is negative, divided by a positive is negative. Making this true. That's good. And case 4, last but certainly not least, let's use x is equal to 6. So we get 6 minus 5, 6 plus 1, 6 minus 2, be less than or equal to 0. Positive, positive, positive. If we take the product and divide, that gives you a positive value, which cannot be true. It cannot be less than or equal to 0, which is false. Getting this x. So our solution is the union of case 1 and case 3. In interval notation, our solution would be from negative infinity to negative 1. Let's include negative 1. And the union, it's not a proper union between 2, round bracket, to 5, close bracket. And you guys can tell me why I chose the appropriate brackets to have a square bracket here, a round bracket here, and a square bracket here. But yeah, that's all for today's video. We reviewed the equations or the rules for inequalities. We talked more about them, how to kind of deal with them. Then we went over some example problems ranging from relatively easier problems to a bit more involved and challenging problems. So if you liked the video, leave a like, comment, or subscribe, and I'll see you in our next video where we start our discussion on absolute values.